All right, so let's continue with our MATLAB discussion, MATLAB Fundamentals, and just a quick recap. Let me, in this matrix of your names, I'm going to go down the second row, and in position 2-1 is Logan. Is Logan around? You have multiple Logans? Oh, wow. Logan Bird.
Yes.
All right, and your name is Logan?
None.
All right, so we have two Logans. All right, so if I was about to type in a matrix into MATLAB, so give me a 2x3 matrix and give me some numbers in it.
2x3?
Yeah.
2, 4, 6.
Mm-hmm. So if I was typing it into MATLAB and I want MATLAB to save that variable, what will I do?
Okay, let's just call it
A. What else? Okay. A is equal to?
Bracket 2, 4, 6, semicolon 3, 6, 9. And bracket.
All right. So this is my 2x3 matrix. If I enter it, basically it's going to display it here. And it also shows up, here you have workspace, so it shows up in memory. If I was going to do a transpose of that matrix, what would I type into MATLAB?
A apostrophe.
All right. So A apostrophe, basically what it does, my first row becomes the first column, and my second row becomes the second column, and the other way around. Okay? Now, if I just type in A apostrophe, okay, it's not going to be necessarily recorded in memory, it's just temporarily displayed as a result. Okay? And here it's going to temporarily record it into this ANS answer, but it's not going to remember it. The moment I enter something else, it's going to go away. Now, before I actually move on, I'm going to actually start recording this. So I'm going to say lecture 2, MATLAB Fundamentals. And today's date is 3rd. So this diary function is basically just going to record everything that I'm typing into the diary. So I'm going to retype A and A prime. Okay? So if I wanted to store A prime as a variable, I would have to give it another name. Yes?
Could you save it after you've done all your commands? Like go back?
You could go and copy with your mouse and copy into a file. Yeah. You could also sometimes, you can also pop up a history here. So I don't have it set up that way, but you can add one more thing that will show history of the commands, and those are easier to kind of cut, copy, and paste. So yes, you could, as long as the MATLAB is open, this kind of scrolls, and you have access to everything that is recorded. I don't know if there is a cutoff. So if you keep MATLAB open for 30 days, and for 30 days you're typing something, and at some point you're going to start to lose the stuff that you, and that's typically called history length, or some sort of memory that is devoted to that history. So maybe at some point you need to start saving. So good practice is actually to save, and we're going to get to that, to save important workflows that you develop. You save into scripts, and those scripts are saved as files that you can execute again. So we're actually getting there. But for now, we're just doing some fundamentals. All right. So now we will actually continue. So this is just a quick recap of matrices. If I was actually, so let me actually recap also multiplication. So Misha, if you give me a matrix B, so that I will be able to do multiplication A times B.
A is 2 by 3, then we would need B to be
3 by 2, for instance, sure. So give me a 3 by 2.
So open bracket, space, 2, 4, semicolon, 3, 6, 1, 5.
Okay, so this is B. And then if I wanted to do multiplication, I would do A times B. Okay, so this is my 2 by 2 result. I'm just going to briefly go over how does multiplication work if you did it manually, because you have to do it manually. So essentially, this position 2, 2, okay, which is 93 in my result, I get as a dot product between the second row, 3, 6, 9, and second column in B, 4, 6, 5. So it is 3 times 4 plus 6 times 6 plus 9 times 5. Okay. And I can actually double check that. Let's see. 3 times 4 plus 6 times 6 plus 5 times 9 is indeed 93. Okay. So that's how we fill in the matrix values. Okay. So we will now go on and we mentioned some built-in functions last time at the very end of the class. So essentially there is some, if I just wanted to get identity matrix, that is the matrix that has ones on the diagonal, I can type in I and then I need to specify size. If I just kind of want to randomize my output, I can do rand of 3, 4, and we mentioned last time how we can actually, this result, rand of 3, 4, is a result that is between 0 and 1, but you can actually scale it to anything, really. I do believe that there is actually, I think, rand I. So with any built-in function, the way you will actually get help, you will type in help. And so help rand, for instance, will give you a reference information on rand function, okay? As well as there's quite a bit to read here, but these are pseudo-random numbers, and essentially it will also at the very end give you any related functions, and I believe that rand I actually gives, when you click on rand I, it gives integers. So there's pseudo-random integers. So let's give it a try. Rand I of 3, 4. I think that's gonna get numbers. So 3 is the maximum. I think that's what it said. So I max and n. So it's gonna return a 4 by 4. In my case, I typed in rand I 3 or 4. It's gonna return a 4 by 4 matrix with random numbers up to 3, okay, integers. So if you wanted integers for some reason, well, here is a built-in function that does that. But again, you can also program yourself for a function to give you out what you want, okay? All right, so these are some examples of how to get matrix. One of the more common, or most common even, commands that we will use is so-called Linspace. So anytime I'm solving something numerically or designing myself a space to produce some simulation results, I need sort of a sample points. And Linspace will actually give me sample points in a vector, in this case between 0 and 100, okay, and 11 of them. So you can type in this. So basically 0, 100 gives me the limits of my array, so it's an ordered array. And this is how many equally spaced points. Okay. You can also work in log space. So in that case, this is interpreted as 10 to the 1 and 10 to the 5. And equally spaced in terms of the 3 points equally spaced in log space again. So times 10 times 10 times 10. Or times 1,000 really. And anytime, we already mentioned this, anytime you have a matrix or an array, you can check on its size by typing size. So let's try, I'm going to say x, I'm going to store this in linspace of 0, 100, 11. So size of x is 1 row and 11 columns, so that's a row vector with 11 elements. Questions? So again, remember Linspace, very useful. I think if you saw a lot of times, the way these functions are coded is that you can call them, this function Linspace or rand or any other, you can call in multiple ways. So if you leave out certain information, there is a default that is assumed that the function will still work. So for instance, if I just say Linspace, y is Linspace 0, 100, I think it's going to give me 100 elements. I'm going to check in a moment. So basically, it's going to fill in a default value for how many points in between 0 and 100. Let's see. Yes, indeed, there's 100 columns. So size of y is 100 elements. So 100 is a default value if you don't give it how many points you want. So that's an elegant way to program because that allows us to just do things quickly. But then if you're not aware of what defaults are, then that can bite you later because you were not thinking about it. That is actually a point that is valid for any software out there that you're going to be using. There are certain values that are typically built in or assumed for you to make it easier for you, but at the same time, if something is not working down the road, it might be because of these assumed values. So you have to kind of check in that mind that now it's the time. You will use a lot of software in your life, in your professional life, and always have in the back of your mind noted that that software made certain decisions for you because they're possibly common to assume in the line of work you're doing or anything of that sort. So sometimes when things are not working, it's very good to go back to the whatever assumptions were made to actually go in and solve the problem. Okay. All right. So let's also. Once I actually have things, it's easy when I'm typing things in or reading them in. But I actually want to, in programming, I want to do something with it, and I want to refer to my elements, and if I have arrays or matrices, I want to grab them. So the way you actually do that, that's so-called subscript notation, the way it's programmed. The way we would write A, 2, 3 with the little subscripts 2 and 3. That is, subscripts are extremely difficult in programming. You cannot refer to things by subscripts. So the way you would actually grab an element of A, let's remind ourselves what A was. A of 2, 3, its position in the second row and third column, so it's actually 9. So if I wanted to work with that element, I would, in any programming or in command line here, I would refer to it as A23. If you had actually just the vectors, we had vector x, then I can just grab x of 5. So I can skip the first row. I can actually say it's x of 1, 5, because that's what it technically is. Okay. But I don't have to, if it knows if it's a row vector or a column vector, it's going to skip that 1. So you can just write x of 5. Okay? Uh-huh.
On the Linspace vector, can you change the base so that it's not 10?
Help Linspace and find out for us. Possibly. Whatever you can think of, it's probably already programmed in Matlab. It's been extensively used. So there's a lot of things that I keep learning about knowing, and unless you use them in certain contexts, you will not necessarily know. So he will find out for us if this base of the log space can be anything other than 10. I don't see why not. That's a fairly straightforward change. So how would I actually manipulate this A of 2, 3 that used to be 9? I can manipulate it, and I can just, in my program or otherwise, say, well, I don't like 9. I'm going to put the 90. Okay? This permanently changes A in memory, so now it's changed. I can actually decide to do an entire row, so the way I'm going to actually refer to row 2. This is a very and extremely elegant thing in Matlab that does not necessarily exist in other programming languages, and I wish it were. You can just put colon, and that will basically mean entire row, everything that you can see in this row. You can also do the same for columns. Oh, there's no 4, there's 3. Okay? So third column would be column instead of the row indices and then 3. So that basically refers to the entire column. So basically refer to the A of 3 refers to the entire column 3. I can then also change it as well. So I can say, let my column 3 be 0, 1. Okay. So now I actually changed my entire column to be 0, 1. What will happen, let me go down my second row here, Michael Chen. So Michael, what will happen if I actually type in 0, 0, 1? What do you think? Probably, let's actually check that in a moment. So basically this is the size. There are 2 elements and I'm assigning something that is 3. Matrix A cannot accommodate that. Okay. My 2 options technically, so somebody has resolved this issue, is A, report an error and say, no, you can't do that. Second option could be to fill in zeros. Okay. Let's see what does Matlab do. It cannot do that. Okay, and this was the sound. I'm going to mute my computer or else you'll hear errors. So there is a dimension mismatch. Okay. So make errors and don't be upset with making errors. Okay. Because that way you will learn what you can or you cannot do. There's one thing, especially if you're just a beginner programmer, you will see me just typing things very quickly and producing a code here within 5 minutes, right? Well, it's something that I've been doing for a while, for one. And it's something that I prepared for because I came to teach a class. Okay? There's a lot of things that I'm fast in, but nevertheless, to this day, I type in a lot of errors. And debugging or weeding out errors is a part of the normal process. It's frustrating, okay? But it's often 90% of the time in coding is weeding out errors that you type in, even if you're very experienced. So you just, with experience, you become good at catching yourself and setting up the framework so you can go and double check yourself constantly. Otherwise, we're humans, we make errors, okay? So don't be frustrated, just take the time. It's the time that everybody has put in. I can tell you from my beginning introduction to numerical class, I was programming Gaussian elimination, which we will get to in systems of linear equations, and it took me an entire 4 hours, and that's actually a good day when you actually find the mistake, to realize that instead of letter L, I typed in 1, and I didn't see it on the screen. So because of that, I was producing this error that I could, the program worked, it was just giving a crappy result because of that. Simply because instead of L, so it's something that is out there, okay? So just go line by line and fix things as they go. All right, so this is the column notation that I started working on. So I can use column in multiple ways, okay? One I just gave you, basically column means everybody, or it means everybody between limits. So if I omit the limits, then it means just everybody. Or I can put the limits, and I can use it in multiple ways. So I can actually define a vector with column notation. Just 1 column 10 will give me numbers spaced by default by 1 between 1 and 10. Okay? And I can refer to my matrix elements that way using that notation as well. So I can actually say A of 2, 2. Okay, so this is basically, in this case, I have a 2 by 2 matrix, so this is just 1 and 2, but this is the same as saying elements between 1 and 2 in third column. Okay, I could have done this as go to second row and just takes elements between 2 and 3. Again, I have a small matrix, so between 2 and 3 is not a big deal. But this is my 2 elements right here. Okay.
Oh,
So basically what this colon notation, this is basically a vector is created, which is just 2, 3, and that's placed into my position. Yes, question?
so the colon thing.
Yes.
Is that how colon?
Hmm?
Yeah. So the colon, it just like takes all the terms between those two. So if you did like 1 and 3, you get 3 terms.
Yes. Yes. So you could do 1 to 3. This example that I just showed on the slides was 1 to 10. Okay. Now I cannot use it. I cannot use 1 to 10 in matrix A because I don't have that many rows. So index exceeds matrix dimensions. Right? Yes.
When you're defining like the step, the increment between numbers, does that have to be an integer or can it be decimal?
So by default here is an integer. Okay. But I could actually say 1 to 0.5 2. And then I'm going by 0.5. So this is expanded way to use colon notation. So basically, I'm going to add step. If I omit step, step is 1. Okay? So this is this default behavior. Now, of course, if I actually now try to use this as indices in matrix A, that's not going to work because I cannot go by 0.5, right? Oh, wow. What did it do? Apparently I can use it. I just now learned something else. So it seems that it possibly interpolated things in between or repeated something too. It took 0.5 as a 0.
Those are the actual values.
What happens if I put 0.3? Yes, so I think it just 0.3, that's rounded to 0, so it just repeats a 0, 0. That's rounded to 1. Wow. So it rounds numbers and repeats as many times as you want. Well then. Okay. I learned something new. I didn't think that it would round things.
Wait, what just happened?
So what happened here, this 1 to 0.3 to 2. That's what I passed. So it said, okay, I can do row 1. I can do row 1. But in the position in row 1. 1.3 I can't do, but I can round it up down to 1. This is rounded to 2, and this is rounded to 2. So just repeated first position twice and second position. So what it really took it as, so you can actually do round of this is 1, 1, 2, 2, and that's what it operated with. So these are these default behaviors, which I apparently didn't know about, okay, that are built in. I thought that it's going to give an error. But instead, it rounded and moved on. Okay? So round is actually a built-in function, so round will give you 5.6, it's going to give 6, and at 5.1, it's going to give 5. Okay, so it's a rounding of numbers. So there's most of the mathematical functions are built-in functions, and we're going to use them as, or find them out as we go. Okay. So basically, this colon notation is really powerful. It makes you type things really quickly. Again, you can specify the step. The step can be anything, as long as it's a real number. I could do negative steps as well. So let's just quickly give that. So basically, I can go 4 minus 1, 1. So I'm going to go down from 4 to 1. I cannot necessarily do this. It's going to give me an empty matrix because I cannot, 4 is larger than 1, so I cannot do increments of 1. Okay. Did everybody have the time to type things in? Type in things in as we go because that's your additional practice. All right. Now we will actually do some operations with and beyond the multiplication. So multiplication we already did. I can define my matrices, and as long as my sizes are correct, and basically my inner dimensions, so-called inner dimensions match, then I can do the multiplication. And all I do in Matlab is I type in times. Matlab here, and I'm going to issue a warning, is much more user-friendly than any other programming language out there. Okay? Than any other programming language, you will have to call a special function. You couldn't just type in times. Okay? So times here, this simple sign times, is kind of programmed to recognize, am I working with scalars? If it's just numbers 2 and 3, 2 times 3 is 6. Okay. But if I'm working with matrices, I'm going to actually do a proper matrix multiplication, which is a program that we will actually learn how to program later on. So not all programming environments are this nice. Okay. Dot product is another one that we can do. So type in these two vectors u and v. And u times v is if your vectors are in the correct sizes and forms, u times v is actually going to give you a dot product. So give it a try with these u's and v's. So size of u is 1 times 4. Size of v is 4 times 1. My inner dimensions match. So if I type in u times v, it's going to be interpreted as a matrix multiplication. Yes?
So we just tried multiplying the transpose of each vector, and for some reason it gave us a 4 by 4 matrix.
Yes, that's we're going to get into this. So u is 76, right? Because I have 1 times 4 and 4 times 1. If I do v times u, okay, I have a 4 by 1 and 1 by 4. Result is 4 by 4.
I thought that multiplication always resulted in a scalar.
But this is interpreted, so when you type in times, it's matrix multiplication. So it interprets things as matrices.
So if our result were a matrix, that would be incorrect because it's not.
It's not a dot product. Okay. So this times, so that's a great point to make. So is matrix multiplication. To give a dot product correctly, you have to have a row vector times a column vector, and then you're going to get a dot product.
So would we ever want the matrix results, or is that just overall incorrect?
You could have an application that you want a matrix, but not if you want the dot product. There's something that is safe. You have to have, you have to have row vector times column vector. There was a mismatch in dimensions, yes. However, if you just u dot uv, that's 76, and dot vu is 76. So dot product has multiple ways to define it. I can define it just as if I have two vectors that have they're the same size, I can go and do multiple and create a dot product as the first element times first element plus second element times second element and so forth. Okay. So there are two ways to define dot product. Yes.
Just to be clear for pictures. So if I have a 4x1 and a 1x4,
If I do my matrix multiplication, then the result is
would be 4x4. So even if they're both vectors,
Mhm.
I still get a matrix if I
And-
multiply them together, and that's like what we
That's-
did on homework.
I asked for a dot product. So in that case, you have to have actually first element.
Okay, good.
Okay.
Okay, just
So you
making
have to
sure.
transform things to actually get the dot product.
Okay.
So dot product has one of the interpretations as a matrix product, but it can be just defined on its own. First element times first element plus second element times so. So there's a definition by some. So you have to be in a correct form. So how about you do this exercise? So type in these two vectors and compute angle. And you can choose to do it both ways.
So just to like make sure, if you want to take the dot product of two vectors, they have to have the same dimensions.
Yeah.
And there's like no.
As long as they have the same dimensions, actually mathematically, they're supposed to be two all column vectors or all row vectors, but as long as the dimensions are same, I can do it on row vectors as well.
Yeah.
Though if
And
you
then, like,
took that U transpose V
that would work.
notation, that doesn't work for row vectors. It works only for column vectors.
Yeah.
So in that case, you would have to do, if you had row vectors, you would have to do U V transpose.
And the product always has the same dimensions as like the.
For dot product or the scalar product of vectors, the result is scalar. It's a number, a number.
Oh.
So it has to be one by one.
Oh. Okay.
But if I had matrix multiplication, I can define it on a column vector times row vector, in which case I'm gonna get a matrix that is larger. Okay. Everybody clear on differences? So to compute this angle, you will need the dot product that we just did, and also you will need the norm of vectors u and v. And I'm gonna help you with saying that square root function is SQRT. SQRT, yes.
There's one function.
There's a norm function too. There's plenty of functions. You can just do, so that's basically square root. You can also do norm, but I wanted you to do a little more work with SQRT. Oh, and to get an angle, you need inverse cosine, which is A cosine, and A cosine D. D is in degrees, otherwise you get radians.
Yeah.
A cosine D, that's gonna give degrees, otherwise you get just the radians. This is the formula. Has everybody managed to? The magnitude, the norm?
Yeah.
Yes, it's called norm.
Oh.
If you can think about it, it's probably programmed in already. And then the rest is just finding it in help. So try the most logical name like norm and try to do help norm. If that's the case, and you will see that the function is in there. Matlab also has extensive help online, so if you type things into a web browser, it's probably going to point you to Matlab help. So has everybody gotten a chance? Nick? Is Nick here? So did you try to... so I'm going to type things in. Okay. So how will you get the dot product of u and v? Which method did you choose, Nick?
The dot u function.
Dot, okay. And then I need norm, right? So that's, then I need to divide by norms. So how did you get norm of u? There's multiple ways to get norm of u. What did you choose?
I just did the norm parenthesis u. And then did the norm
Okay.
parenthesis
Are you sure that it's the norm too? Okay. So you have to check help norm, okay, and see what the defaults are. There's multiple norms, as we learned. Okay. So actually, you were lucky here, because norm of u is the same as 2 norm, because that's the most common one, right? But my point is that you kind of have to make sure that that's the norm. Okay. You can also do square root of u of 1 times u of 1 plus u of 2 times u of 2 plus u of 3. And it's obvious why this is not the preferred way, but it's correct. Okay. Another way is to say square root of, well, what I typed in is actually dot product of u and u. Yes? So there's multiple ways to solve this, which is the nice thing. So basically I'm just going to give this a value b. B is a dot product between u and v, and then I divide by norm of u times norm of v. Okay? And a cosine, and I'm going to express it in degrees, so a cosine d of b is about 49, so about 50 degrees. Yeah? If I did it in radians, it's about 0.87. Okay? All right. Okay. Now, we already have learned about some niceties of Matlab and how it kind of assumes things for you, for better or worse. And one of them is also that a lot of functions, if they can be naturally extended to just apply to every vector element, they are. So if I was actually doing a cosine or cosine or any other function that is built in, you can actually do cosine of x where x is a vector, and it's just going to go and compute for every element of that vector. So give it a try. Type in x. This is x. X has values between 0 and p, and the spacing is pi over 4 or p over 4. Okay. So this should be the result you get. And then if you plot cosine, now this is just a quick, we're going to get to the plot. So my x is 0 to, and my y is cosine of x. We're going to get to plotting quite extensively, but this is just a quick introduction to plotting. You could actually plot this, plot xy, and you will get something like this. It does not look like your nice cosine function between 0 and pi because you're very crude here. Maybe we need to put 40 here so I have more points. What I'm doing when this shows up, I'm actually going with arrow up on my computer. If I go on arrow up, I go to all the previous. So my plot of xy, oops, where's my figure now, is a little smoother if I put 40 points there. So if I plot for only 4 points, it does the linear sort of a straight line between every 2 points. So that looks really crude. It's still doing the same in plotting here. It's a straight line. It's just that the points are so close that it looks smooth.
What did you use as your step for that? What did you use as the step?
Pi over 40. So just 10 times, tenfold, right? You can push it. You can go to whatever you want.
How'd you do that? How'd you get that thing
To open, I just said plot xy. So you get yourself x, you get yourself y, and then plot. Now I can also close it. I'll say close all. So if I just do plot of xy, the window will pop open.
How would you superimpose one graph on another?
Hold on.
There's the on.
Okay. Now we're getting ahead of ourselves. You say hold on. And you say z is sine of x. Okay? And I'm going to say plot xz. Haha. I can do that too. Beauty of Matlab, you can do things. I could just close all of it. And I can say plot x, y, x, z. Plotting is our topic next time, but oh well. I just wanted to sprinkle it in here because if I mention it multiple times, it's gonna actually stick. Okay, so this is just a very quick plotting introduction. Couple of more things. One part of this vectorization, or operating on arrays and vectors and matrices, element by element, is that for every operator, such as times, I have A times B, that's my matrix multiplication. However, if I say A dot times B, then it's actually going to multiply element by element. So I'm going to have 1 times 9 is 9, 2 times 8 is 16, 3 times 8 is 21, and continue. 4 times 6 is 24, 5 times 5 is 25, and so forth. So A dot times B is element by element operation. A times B is our classical matrix multiplication. So please type this in as our last example today.
When would we want to use that?
Let's say that you're going to actually have a homework assignment of similar sort, but we know that we can compute permeability based on porosity, right? It's a function of porosity. So if you have porosity, it's actually as per Carmen Coseni, it's porosity to the cube divided by 1 minus porosity squared or something of that sort. So if I wanted to do that on my matrix X, actually we can do this example. So my X is this, or I'm gonna, okay, and I'm gonna divide by 10, so I'm gonna pretend this is porosity, okay. So if I wanted to do X cubed divided by 1 minus X squared, element by element, I'm just gonna put dots. This way I can't do it because it's a vector. I don't know what to do with X cubed. But if I do element by element, okay, so then I can, and I made a mistake of not putting dot here. Now it actually worked on element by element and it applied the same formula to the entire vector. If I'm processing porosities coming from a well log where I have 3,000 of them, helpful. Okay? So I can compute permeability basically in one line. Okay? So that's where you would use it. Okay? Where you want to speed up something. But just to, what was my A? I can add a third row here. Okay? So this is my A. A dot times A is this result. A times A is something else. Okay? This is essentially A squared, where every element is squared. Okay. I could also say A, so every element is squared. Okay. Yeah? All right. See you on Friday.